we were discussing about the existence and uniqueness problem. Uniqueness and existence problem, and in fact what we have shown is that if X be a inner product space and M be a non-empty convex subset which is closed, convex and closed subset, then for any point x belonging to capital X, there will exist a point y in capital M such that the infimum of this x minus y n, where y n belongs to, or y bar belongs to M, will exist, and in fact it will be x minus y. So, this result we have seen when M is considered to be a non-empty convex closed subset, convex and complete. This is complete in the metric defined by the inner product. Now, this result, in this result, even if we change M, instead of taking the convex set, if we consider a subspace which is complete, then also one can prove the result. So, we have the next result where M is replaced by a subspace of X which is complete, or complete subspace of X. So, we have this result, let X be an inner product space and let capital Y be a complete subspace of X. Okay. Let X is fixed, belongs to capital X, is a fixed point, suppose. Then what this result says is, then the vector Z which is x minus y is orthogonal to y. So, basically what is the meaning is that if suppose we have, this is our y, here is x, this is our say x, then we are getting a point y here such that this vector x minus y is perpendicular to y, is orthogonal to y. It means, suppose this is origin, and if I join this as a vector, then this vector x minus y, this vector x minus y will be orthogonal to y. So, this revise or this and this confirms our previous hypothesis that if we want to find a shortest distance from a point x to the set M, then it can be obtained by dropping a perpendicular from x to that point, is it not? So, that gives the confirmation for that hypothesis which we had in mind, clear. So, this is true. The proof is simple. What we are interested is the vector x minus y should be orthogonal to y. Okay. So, suppose the z which is x minus y is not orthogonal to y. Let us prove by contradiction. It means once it is not orthogonal to y, so by definition of orthogonality, a point x is said to be orthogonal to A if the inner product of x a is 0 for all A belongs to A, is it not? That is the orthogonality of x. We say x is orthogonal to A means the inner product of x a is 0 for every A belongs to A. So, when we say x is not orthogonal to A, it means there must be some point available in A whose inner product with x will not be 0. So, let us suppose Z is not orthogonal to y. So, there exists a point say by 1 belonging to capital Y such that the inner product of Z comma by 1 which is say beta is not equal to 0. Okay? If it is now, clearly this by 1 clearly this by 1 is be different from 0 will be different from 0. Why? Because if it is 0 then this inner product will be 0. So, a contradiction. So, it cannot be 0. Okay? Otherwise, the inner product of Z by 1 will be 0, a contradiction. Okay? Will not possible. Okay? So, let us assume that the inner product Z by 1 is beta which is not 0 where y 1 will not be equal to 0. Okay. Now, consider for any scalar alpha the norm of Z minus alpha by 1 whole square. Clear? So, this can be written in terms of the inner product as alpha by 1 comma Z minus alpha by 1, and this will be equal to inner product of Z Z, then minus alpha times by 1 inner product of Z minus alpha by 1 for Z, and then Z inner product of alpha by 1. Is it okay or not? Clear? Now, this Z comma Z and then this Z we are putting here taking minus sign outside, and then minus alpha by 1 alpha outside by 1 comma this. Is it okay? So, I have put it the sort. Okay. So, Z Z minus alpha y 1 Z minus minus plus alpha alpha bar by 1 inner product minus alpha bar inner product of Z by 1, or this can be written as norm of Z square minus alpha by 1 comma Z. So, by 1 comma Z, is it okay? This is comma, okay? By 1 comma Z plus, if I take alpha outside, then what we get is alpha times norm by 1 square minus Z y 1 inner product. Okay. Now, since alpha is our choice at our disposal, so choose alpha such that this portion becomes 0, alpha norm of by 1 square minus inner product of Z comma by 1 is 0. So, what we get alpha becomes inner product of Z by 1 divided by norm of by 1 square. Substitute it again back. So, we get norm of Z minus alpha by 1 whole square is equal to the norm of Z square minus, if I substitute this thing, it becomes Z y 1 into by 1 Z divided by norm of by 1 square. Is it not? By 1. And this will be equal to norm of Z whole square. Now, Z by 1 is beta. So, we can write this beta and this is beta conjugate. So, we are getting minus mod beta square over norm of by 1 square. Now, this is non-negative, this is non-negative. So, obviously, this is less than, strictly less than norm of Z square. Is it not? But norm of Z is, what is our this Z? If you remember the previous result, the previous theorem which we have had earlier, in this case this delta was this, and in fact, it is nothing but the norm of Z. So, this will be equal to delta square. So, this entire thing is less than delta square, but what I claim is 1 is not possible. Okay? but we claim 1 can never happen. Why? Can never happen. Why? Because the reason is, what is z minus alpha by 1? Z is x minus by minus alpha by 1. So, norm of this, now this is equal to norm of x minus a by 2, where y 2 is equal to y plus alpha by 1 belongs to capital Y, is it not? Now, delta is this, the infimum value, this is our delta. So, if we replace by any other point in this set, then it will be greater than or equal to delta. So, basically this you are getting greater than or equal to delta. So, norm of this will be greater than equal to delta, therefore, square will be greater than equal to delta square, but here we are getting strictly less than delta, strictly less than delta. So, this contradicts 1 and 2. So, 1 and 2 shows contradiction. Therefore, our assumption is wrong. Therefore, norm beta must be 0, that is, the inner product of z y is 0 for every y belongs to capital Y. So, x minus y is perpendicular to capital Y. That solves. Is it correct? So, this gives the result. Now, we are interested, these two lemmas will be helpful in giving the idea of the projection theorem. What we are interested in, that we wanted to express the Hilbert space H as a direct sum of the two subspaces. One is closed, another one is the orthogonal complement of Y, and this is called the projection theorem. Any vector space, if you look, the any vector space, elements of the vector space can be expressed as a sum of the two subspaces, but this may not be unique, the representation may not be unique. But if the representation is unique, then we say this is called the direct sum of the two space y and z, and the intersection of y and z will be 0 theta. That is what. So, what we are interested is, we are interested to represent a Hilbert space H, Hilbert space H as a direct sum, as a direct sum of a subspace of a closed subspace, I think of a closed subspace Y and its orthogonal complements. Orthogonal complement. This is our interest. That is, we want H to be the direct sum of y and y perpendicular, where y perpendicular is the set of those vector in H such that z is orthogonal to y, okay, orthogonal complement of y. Okay. Now, the idea of the direct sum, you know, when any element of H can be expressed uniquely as a sum of the two elements, well, first belongs to y, another belongs to y perpendicular. And in particular, when this is a one is the orthogonal complement of the other, then we say it is a perpendicular to y. Okay. So, we are interested in this. Now, this result is known as the projection theorem. So, what is the projection theorem is? let Y be any closed subspace of a Hilbert space H, then Y H can be expressed as a direct sum of Y and Z, where Z is orthogonal complement of Y, where okay. So, come okay. Let us see the proof. Now, since H is complete because it is a Hilbert space and Y is closed, this is a closed subspace of H, and we know the result. Every closed subspace of a complete metric space or complete norm space, Banach space is Banach, all Hilbert. So, Y is complete. Is it not? Further, being by a subspace, it is convex. Every subspace is a convex set. So, we have H as a vector space, Y is a subspace of a vector space which is non-empty convex subset of H and complete. So, by the uniqueness and existence theorem, we can always find a point in Y which is nearest to X by dropping the perpendicular from X to Y. Okay. So, by the previous result, previous theorems, is it not? By previous theorem, for every X corresponding to every X belong to H, there exists and Y belongs to capital Y such that the Z can be written as X plus Y, where Z belongs to capital Z, which is the Y orthogonal. Is it okay or not? Z will be, oh sorry, I am sorry, this is X, X will be Y plus Z, because every X can be expressed in this form Y plus Z, where the Y belongs to capital Y and Z belongs to orthogonal complement, or X minus Y will be orthogonal to Y. This is the, so by using the previous result, we can say that every element X can be expressed as a direct sum of Y and Y orthogonal complement. Now, if this is unique, then it will be the direct sum, because this representation is okay, but if it is also unique, then we say it is a direct sum. So, for the uniqueness, suppose there are two representations. Suppose X is equal to Y 1 plus Z 1 as well as Y 2 plus Z 2, where Y 1 Y 2 belongs to capital Y and Z 1 Z 2 belongs to capital Z, that is Y orthogonal. Okay. So, what will be, this will imply Y 1 minus Y 2 is the same as Z 2 minus Z 1, but Y 1 and Y 2 belongs to capital Y. Y is a subspace. So, Y 1 minus Y 2 will be the element of Y, but Z 2 minus Z 1 is a point of Y orthogonal complement. So, Y 1 minus Y 2 is also the point of Y orthogonal complement. Clear? So, it means they are the common element of Y and Y orthogonal complement. Is it not so? So, they will belongs to the Y intersection Y orthogonal. Is it correct or not? So, once this is there, but Y and Y orthogonal complement, it is null. So, which is null because representation is unique and direct sum. So, it is 0, Therefore, by 1 is equal to by 2. Similarly, z 1 is equal to z 2. So, representation is unique, hence we get this. Okay. So, projection theorem proof is very simple, just 2 line. Now, what is the consequence? How to get it that represent? If we have this plane, suppose we are having this plane and here is this point x, then this is the vector x, say here origin. Then when you project it on this plane, you are getting this vector y equal to p x. Clear? Say for example, if I take x to be xi 1, xi 2, okay, and then I want to project it here. So, this point is xi 1 0, which is by x. Now, if I project any point by on perpendicular on itself, then it is nothing but the same elements. Clear? Any point on this under the projection where the second coordinate becomes 0. So, every point of y will be projected to itself. So, we are getting a projection p x p from h to y, where x point is projected to y, which is p x. Okay? And this projection has the following property. One is h p from this will be on to y, and then this projection from y onto itself, any element xi 1 0 will be projected on it, and z will be by orthogonal onto singleton set 0. If I take the point here, then what is the projection here is 0 xi 2. So, it will be 0 0. So, this will project on this. It means the p square becomes p, because p square x is equal to p of p x, and p x is equal to again x. So, we are getting this, okay, p x. P of p x becomes p x. So, this will be there. So, p square becomes p, that is it is an idempotent operator, bounded idempotent operator. So, this gives the idea of the projection, that if you want to project the closest element, the shortest distance, then from a set, then it can be obtained by dropping a perpendicular from x on this space, okay, and that projection will give. Clear? Now, this also gives a concept of annihilator. This definition, a new thing is annihilator. An orthogonal complement of M, which is not is denoted by in an inner product space X is the set X belonging to capital X such that X is orthogonal to M, is it not? And this is known as an annihilator. A special name is given, orthogonal complement in inner product space, we call it to be M perpendicular, denoted by n called the annihilator. And this annihilator is obviously a sub vector space. This is so clearly M perpendicular is a vector space. Why it is vector space? Yes. So, basically we are defining the annihilator as, because this as a note you can say that will be more clear. M perpendicular is a vector space. Okay. So, x belongs to M perpendicular if and only if the inner product of x b is 0 for all b belongs to M, for all v belongs to M, is it not? So, using this we can say, suppose x and y are the two element belonging to M perpendicular. So, find out alpha x plus beta y and then v, then you will see alpha of x v plus beta of y v, and each one will be 0. So, this is a vector space. Now, second one is this M perpendicular is also closed. This is a closed set subspace. Why it will be closed? Let us take a sequence x n belongs to M. So, we get inner product of x n v is 0. Now, let the limit of x n is n x. If we show the x belongs to M perpendicular is fine. So, let us consider x n minus x v. Okay. Now, this will be equal to x n v minus x v. Now, take the limit as n tends to infinity. Since inner product is a continuous function, so this left hand side will give 0 into v. Okay. Clear? And that will give the corresponding 0. Okay. So, here we are getting x and b will tends to, this entire thing will go to 0, is it not? So, this entire thing will go to 0 implies that x n v inner product this will go to x b. Okay. So, x must be a point in the M perpendicular. Okay. So, that will give the closeness for this. Okay. Is it clear or not? Then another exercise, as an exercise you can say, always M is subset of M perpendicular perpendicular. Why? Because if suppose x belongs to M, then this implies that x is orthogonal to M perpendicular. If x is orthogonal to M perpendicular, then it must be the point of what? Orthogonal complement of this. So, that is nothing but the x belongs to M perpendicular perpendicular. So, that is why it is subset. Okay. So, these very things are now as an exercise you can note, and we will do it if it is not coming, but this is interesting as an exercise. The first is, if y is a closed subspace of a Hilbert space H, then y is equal to y orthogonal. We have the equality sign provided the subspace y is closed. In general, y is subset of y perpendicular perpendicular, but equality holds if y becomes a closed subspace of it. So, this is another exercise which is that for any subset M which is non-empty of a Hilbert space H, the span of M, the span of M is dense in H if and only if M orthogonal complement of M is a singleton set 0. Okay. So, these two I am just leaving, and next time if it's, we will discuss the proof if it is not solution, if it is not possible. Okay. So, that is now after this concept, as we have seen that orthogonal complements or orthogonality plays a vital role, and it simplifies the many things, is it not? Even for the over the linearly independent sequences, we have a advantage of the orthonormal sequencing. The reason is, suppose we have a vector space, say x equal to say R 3. Then we say no, if x can be expressed as alpha E 1, alpha E 2, alpha E 3. Well, what is E 1, E 2, E 3? These are the basis element of this vector space R 3, where E 1 will be 1 0 0, E 2 will be 0 1 0 and E 3 will be 0 0 1, is it not? So, basically these three vectors which are the basis element for R 3, they are at right angle to each other, clear. So, this collection E 1, E 2, E 3, this is an orthogonal set. Orthogonal set means a set is said to be orthogonal if we pick up any two elements, then the inner product of these two must be 0. That is, they are at right angle to each other. Okay? Any pair will be orthogonal to other. So, the inner product of E 1 E 2 will be 0, inner product E 2 E 3 0, E 1 and E 3 will be 0. So, they are orthogonal. In fact, the norm of each element is 1. So, we will call it as a orthonormal also, that we will come in. So, any element x belongs to R 3 can be expressed in terms of the basis element. Now, here this basis element has a peculiar property, they are at right angle to each other, but it is not always true that all the basis element must be orthogonal to each other, it is not true. But what here is, because it has a perpendicular property, orthogonality property, the advantage is, if we are interested in finding the constant alpha 1, alpha 2, alpha 3, then just take the inner product. Suppose I am interested in alpha 2, take the inner product with E 2. What happens is, alpha 1 inner product of E 1 E 2 will be 0, alpha 2 inner product of E 2 E 2 will be 1 and rest will be 0. So, without any effort you can just find out the constant alpha 1 alpha 2. Otherwise, in a general example, when the vector space is given and it is required to find the set of the vector are linearly independent, what you require, you go for the lengthy calculation and all the 5 equations, solve it for alpha 1, alpha 2, alpha 3 etcetera, and then if all alphas are coming to be 0, we say the set is linearly independent. If it is not, then we say it is dependent. Similarly, any vector space you wanted to find, then this will be the problem. But in case of the orthogonality, the problem situation is much simpler. Another advantage, or suppose I wanted to introduce one more here, say alpha for E 4, okay, and I wanted to get this linear combination E 1, E 2, E 3, E 4, any element belongs to that linear combination. So, I required only one extra constant alpha 4, and that will be simpler if I deal with the orthogonal set of orthogonal elements. So, study of the orthogonal element or orthonormal elements simplifies the situation in case of the inner product space, clear. So, we will discuss what is the orthonormal sequence and orthonormal sets. So, let us say first definition of orthonormal sets. And sequences. Okay. An orthogonal set M, an orthogonal set M in an inner product space X is a subset M of X whose elements are pairwise orthogonal. pairwise orthogonal. Then an orthonormal set M, which is a subset of X, is an orthogonal set in X whose elements have norm 1, that is, for all x y belongs to M, the inner product of x y is 0 if x is not equal to y and 1 if x is equal to y. Clear? So, that is now, if a set M orthogonal sequence, if an orthogonal or orthonormal set M is countable, then arrange these elements, arrange its elements in a sequence, say x n, and call it orthogonal or orthonormal sequence. Orthonormal sequence. Is it okay? Means same set, if the set is countable, then arrange it in the form of the sequence x 1, x 2, x n, and then this collects sequence will be called as the orthogonal sequence if the elements are orthogonal, means pairwise disjoints only, or orthonormal if apart from the pairwise disjoint each one is having the norm 1. So, that we can get the corresponding orthonormal sequence. Okay. Now, say for example, if we look this equivalent space R n 3 that I have already discussed, the set M which is E 1 1 0 0, E 2 0 1 0, E 3 0 0 1. This is our orthonormal set, is it not? Each one is having norm 1 and they are at right angle to each other. Clear? Then if we take x to be say L 2, it is a inner product space, then what is the orthonormal sequence? Yeah, that is also E 1 1 0 0 0, E 2 0 1 0 0 0 and continue up to infinity. That will be the collection of the orthonormal sequence. Now, suppose we have the set another set C A B, set of all continuous functions, let x C A B will not form a inner product space. Okay. So, let us take the another x, let x subset subclass, let x be the inner product space of all real valued continuous functions on the closed interval say 0 to 2 pi, okay, with inner product defined as inner product of x by as the integral 0 to 2 pi x t by t dt. This will form an inner product we have seen already. Okay. Now, an orthogonal sequence in this case, we claim that u n t, which is cos of n t, okay, or v n m t, suppose sin of m t. These will form orthogonal sequence in X, because if we take the inner product of u n u m, just u n, then what we get is 0 to 2 pi cos n t cos m t dt, and we know the value of this will be equal to 0 if m is not equal to n, because when m is not equal to n, then twice cos of cos b formula. So, it will give sin, and then when it integrate it, we get the value 0, and equal to pi if m is equal to n, equal to 1 2 3, and equal to 2 pi if m is equal to n equal to 0. When both are 0, it is 2 pi. So, basically this u m, the inner product of this will be 0 when m is not equal to n, clear, and when m is equal to n, you are getting something else. So, we are not saying that this is a orthonormal sequence, but it is a orthogonal sequence, and if you are interested in finding the orthonormal sequence, from here one can find orthonormal sequence as follows. Say the first element of this E naught t, I am writing to be 1 upon root 2 pi. So, E naught will be, norm of E naught square will be 2 pi, that will be get cancelled. So, 1. Then E n t is u n t divided by norm of u n t, and that is equal to cos n t over root pi. Okay. So, we are getting this sequence not only orthogonal, but each one norm of this will be 1. So, it formed. Similarly, V n will form. Similarly, V n will form the orthogonal sequence. Okay. So, that now, if we look this sin n cosine t, is it not a terms of the Fourier series, because any Fourier series expansion x t can be written as a naught by 2 plus sigma a n cos m t plus b n sin of n t. So, this cosine t and sin n t which are coming, basically they are the orthogonal sequences, and we are representing the x in terms of these orthogonal sequence. Okay. So, as a inner product can be used or can be applied to compute this constant n n b n in case of the Fourier series. Is it okay? So, that is the advantage of this. Now, another advantage of this orthogonal sequence, orthonormal sequence is, as we have seen, that suppose we are dealing with this, let X be a inner product space, X be an inner product space, and let us suppose that y n and even e to e n be an orthonormal sequence, and e n be an orthonormal sequence or orthogonal sequence in X. Okay. Orthonormal or orthogonal in E. Now, y n is suppose a span of E 1, E 2, E n. Clear? Then any element y belongs to capital Y n can be written as y as sigma k is equal to 1 to n alpha k E k, where what is alpha k? Is the inner product of y E k. Okay. Alpha k is the inner product of E. So, this is the general thing. Okay. Now, what we want it is, let us suppose choose fix k, sorry, this alpha k we wanted to change, okay, and so that a new term which you are getting by should come out such a way, so that we get the complement or orthogonal complement somewhere. So, what we are interested is that, let us say for a particular choice of a, we are interested in that, for a particular choice of alpha k, say alpha k is the inner product of x e k, where what is x? Where x is not the element of the span of E1, E2, En, means x does not belongs to yn, x belongs to capital X, that is x belongs to capital X, but x is not the elements of yn. Is it clear? So, what we are, if I replace this alpha k by another value constant depending on x, x e k, then can we get or be for a particular choice of this alpha k, we claim to get an element by in yn such that x minus y will be orthogonal to y, orthogonal to yn. This is our claim. Okay. Why? Let us see how. First thing is, if I replace alpha k by this, then what will be our y? The y becomes sigma k equal to 1 to n x e k, is it not? X e k. This is our y. Now, if I take norm of y square, then we are getting this is norm of y square, means inner product of y by. So, substitute this. So, sigma k equal to 1 to n x e k comma sigma k equal to some other number, let us be m equal to 1 to n x em, is it not? Let it be another number, there is no problem. Now, you take it k equal to 1 to n. So, each term will be operated on this. So, E k when it is operated on E m, when m is different from k, it is 0. So, only the term will be E k will be 1. So, basically what you are getting is sigma k equal to 1 to n x e k is outside, and then another term which you are getting is x e m, is it not, but conjugate. So, we are getting mod of this x e k whole square. Is it okay or not? Did you get on me now? Huh? Because if as soon as I open, this thing will come here. So, you are getting conjugate of it. So, you are getting mod of this square. Okay. Now, we claim that x minus y will be orthogonal to y. Why? Because inner product of x minus y comma y, this will be equal to inner product of x y minus y comma y, and x is y is this one sigma k equal to 1 to n x e k and minus norm of y square. So, this will be equal to sigma, again if I take this thing x e k. So, this conjugate will come here. So, it will be the same as x e k into x e k conjugate Okay. And what is norm by square? That already we have seen, this is the modulus inner product of x e k whole square, k equal to 1 to n. So, 1 to n. So, basically both are 0, both are equal and we get 0. It means that x minus y is orthogonal to y. Okay. So, let x minus y to be z, let x minus y to be z. So, let z stands for x minus y, which is it clear or not? So, what will be the x? Therefore, x will be equal to y plus z. Now, once they are orthogonal y and z, okay, so we get from Pythagoras norm x square will be norm y square plus norm z square by Pythagoras. Therefore, from here we get norm of z square, which is norm of x square minus norm of y square, and this is equal to norm of x square minus norm y means sigma into modulus of x e k whole square, k equal to 1 to n. Clear? Now, since the norm z can never be negative, so this is always be greater than equal to 0. This implies that sigma k is equal to 1, k equal to 1 to n modulus inner product x e k whole square is less than equal to norm x square. Clear? Norm x square, and this is nothing but this is bounded for each n. This is true for each n, bounded above by norm x. So, bounded above. So, this series as n tends to infinity, the series sigma k equal to 1 to infinity modulus of inner product x square is convergent. Is it correct or not? This is bounded for each n, and when the sequence is a increasing sequence, this is bounded above monotone sequence. A monotone sequence which is bounded above must be convergent. Why monotone? Because when you take increase n equal to n plus 1, another positive terms you are adding. So, it is an increasing sequence bounded above. So, it must be a convergent and dominated or bounded by norm x square. Is it correct? So, this leads to the inequality which is known as the Bessel's inequality. What this Bessel's inequality says? Let E k be an orthonormal sequence in an inner product space capital X, then for every x belongs to capital X, the sigma k is equal to 1 to infinity modulus of inner product x e k whole square is less than equal to norm of x square. Okay? And this inner product, this result is known as the Bessel's inequality. Okay? It will be used. Okay? Thank you. Thanks. Okay.